Hi everyone, this is now moving to Unit 2 in our course, and we're going to start looking at different types of annuities. Okay, so annuities kind of a, a broad term, and we're going to talk about multiple different types, but some examples that you're going to see would be a loan for your house, when you have a mortgage, when you have car payments. Okay, they're all examples of annuities. So what an annuity is it's a series of equal payments and they're made at periodic intervals or at predefined intervals. Okay, so the length of time between these payments, whether it's bi-weekly, weekly, quarterly, semi-annually, it's the same terms you've been seeing in our last unit when we talked about future value and present value. That's called the payment interval or the payment period. And the total length of time for the annuity for when you receive payments or when you have to pay payments, depending on what it is known as the term of the annuity, okay? And the amount of each of those payments is known as your periodic payment. You're going to see the term PMT, okay, for payment in the equations that follow. So there's several different types of annuities, but they're broken down by a couple different factors. The first factor that they're broken down by is when the actual payment occurs. So in ordinary annuity, the payment occurs at the end of the payment period. And in an annuity due, the payment occurs at the beginning of the period. Okay? So that is your first defining factor to figure out what type of annuity it is. The second factor to consider is whether it's a simple annuity or a general annuity. Okay, so a simple annuity is just that. The compounding frequency and the payment period are the same. In other words, okay, if you're making payments every monthly, okay, that means your interest is also compounded monthly. All right, so that's a simple annuity. And the first item we're going to talk about in this lesson are ordinary simple annuities. The second option is when your compounding frequency and payment period are not the same. So an example of that could be your mortgage, where your interest is compounded at a different period, let's say semi-annually, but you make bi-weekly mortgage payments as part of your mortgage agreement. Right? That's the other type. So that's when they are not the same. So like I said, in this lecture, we're going to talk about ordinary simple annuities. So the payments are made at the end of the period, okay, and the compounding frequency and payment period are the same. I don't expect you to just see this slide and memorize each of these types right now. We're going to break each one down in our subsequent lectures, okay? So each of these types will be talked about, and like I said, we're only going to talk about ordinary simple annuities for this lecture. So there's a couple special cases, okay, that I'm also going to talk about. Again, I don't expect you to memorize these, but these are just, I call them little quirks that have to do with each case. So the first might be a deferred annuity, and that's when the first payment is delayed for some period of time. A good example of that is your student loan, okay? When you graduate, there's normally a grace period where you don't have to immediately start making your payments. Okay, so usually it's a period, sometimes 6 months, where then you have to start making regular contributions to pay off your student loan. All right, that's an example of deferred annuity. A perpetuity is a pretty rare case, and that's where an annuity, your payments for it continue forever. So usually it'd be payments to you, and it's a certain amount of money set up so that they continue forever. The third one is the one you're going to see most often. It's called an annuity certain. Okay, and all that means is that your term is fixed, so you know the beginning and the end dates. Okay, so car leases, payments on loans, like your student loans, right? You have a defined end date usually. You can pay it off sooner, but when your payment amount is calculated, it assumes a fixed beginning and end date. Another example of that is a mortgage. Okay, if you have a 25-year mortgage, that means it starts from the day you purchase the house, and if you stay in that house for the full 25 years, making your regular payments, then your loan would be paid off. The last type, a contingent annuity, just means that you don't know those. You don't know the exact beginning and end date. Okay, and that does happen in some cases, especially when you don't actually have a set payment plan for paying something off. So each of these will be discussed in certain ways in later lessons. Okay, like I said, I don't expect you to know each one of these terms just from watching this slide the first time. But it is a good piece to come back to when we look at later lessons in the course. So what you've probably been thinking is we're going to look at ordinary simple annuities, and the payments are made at the end of each period, and the payments are the same. So we've kind of talked about that, right? So you think about it, okay? You've got regular payments, say $100, and they're occurring at predetermined amount of times. So let's call this today. And let's say every year, so year 1, year 2, year 3, year 4, year 5, you have a regular payment of $100, okay? And you want to figure out what that value is worth. Well, if you think, oh, I want to know what the future value is, why couldn't you just do the future value of each one of these payments to figure it out? Well, why don't we try that, okay? Let's try an example kind of using that, because I always think in my head as to what we've learned so far and can you still apply that? Well, if you're thinking in this case, we already know the present value of each of these payments, right? Let's call it $100. And if we know the interest rate, okay, and when they're compounded, why can't we just do that calculation? So let's look at an example. Find the future value of an annuity with 5 equal deposits of $3,000, one deposit made at the end of each year. Interest is 6% per annum compounded annually right after the deposit is made. Okay, so there's a couple things to notice here. I'm telling you it's an ordinary simple annuity, but the way you'd know that, all right, is first of all, you see that payments are made at the end of the year, okay, not the beginning. The other thing to notice is that your deposits are made at the end of each year, so one deposit a year, and your compounding period is also annually, okay? So deposits made at the end of the year make it an ordinary annuity, and having the compounding frequency and the payment frequency the same make it a simple annuity. So that's why it's an ordinary simple annuity. So like I said, let's look at this example just from what we have learned so far in this course. So we've got 5 equal deposits, okay, and it says at the end of each year. So like I did in every other example, this is today, and we've got 5 equal deposits at the end of each year. So call this year 1, year 2, year 3, year 4, year 5. So we'll say 1, 2, 3, 4, 5. So you have 5 equal deposits at the end of each year, which means after the first year, we have $3,000. After the second year, we have $3,000. Third year, fourth year, and fifth year. Okay? So we have payments, again, they're equal payments at the end of each year, and we want to find the future value. Okay, so in other words, we're going to want to find, remember back to our focal date, the future value at the very end, right? So this last payment is happening right at year 5, so we know its future value, it's just $3,000, right? Because we know it at that period in time. And what we know is we know the present value of each of these deposits at their specific period in time. So we should be able to just find the future value of each of these payments, just like we did in previous lessons, to give us the answer. Okay? So what that means is that we have to do a future value calculation for each of these 4 payments. Remember, we don't have to do it for the payment in year 5 because that's the focal date that we picked, right? So that means that at that point in time, its value is $3,000. Okay, so there's no interest calculation to add to that. So we have to do 4 separate calculations. So I'm going to call them future value 1, 2, 3, and 4. And these numbers, okay, correspond to the years that I've selected above. Okay? So we know, starting with the formula, that the future value is the present value times 1 plus your periodic interest rate, and that's raised to the exponent n, or the number of compounding periods. All right? Now for each of these, we have to have a different number of compounding periods, right? Because one of them, it goes from year 1 to year 5, and then year 2 to year 5, year 3 to year 5, and year 4 to year 5. So they have a different total number of compounding periods, okay? But in our question, our interest rate was only given once, meaning we have just one interest rate to consider. So for each one of them, we're going to have the present value, and that's times 1 plus the periodic interest rate, and that's, I'm going to place each of them to the exponent n1, n2, n3, and n4. And then again, just corresponds to the number of years. Okay, so where they are in our overall timeline. So that's kind of how I'm relating each of those. All right, so now we have factors we need to figure out, okay, in order to be able to substitute them into each one of these formulas. Okay, so I'm going to go over here to the right side. We know that our nominal interest rate, J, is 6%, which is equal to 6 divided by 100, removing the percentage sign, which is 0.06. We're compounded annually, so that means that M is equal to 1. So our interest rate I is equal to 0.06 divided by 1. Remember, I didn't write the formula, but I is J divided by M, which is 0.06 divided by 1, or just 0.06. Okay? Our last item is we need to figure out the number of compounding periods for each of these 4 instances. Okay? So we have N1, N2, N3, and N4. Okay? So for N1, okay, remember the formula for N is the number of years times the number of compounding periods per year. So for N1, this first payment here, we have to go 1, 2, 3, 4 years. All right? So that means it's 4 times the number of compounding periods per year, which is 1. Okay. For N2, we've got to go 3 years from year 2 to year 5, so 3 times 1. For N3, we have to go from year 3 to year 5, which is 2 years. And for N4, okay, we just have to go 1 year from year 4 to year 5. So that means N1 is 4, N2 is 3, N3 is 2, and N4 is 1. Okay, this is just for the 4 deposits, again, that are not already at the focal date. Okay, so now we have all these values. Okay, the last value I haven't listed here is actually the present value. And for each of these cases, the present value was $3,000, right? That was the amount provided in the question. So I'm going to substitute all these values in. So we have 3,000 times 1 plus 0.06. And for this first deposit, that's the exponent 4. For the second deposit, 3,000 times 1 plus 0.06 to the exponent 3. For the third deposit, it's 3,000 times 1 plus 0.06 to the exponent 2. And for the fourth deposit, it's 3,000 times 1 plus 0.06 to the exponent 1. Now remember, our fifth deposit we already know this value, okay? And that's $3,000, right? Because, remember, the fifth one is at the focal date, so there's no interest rate to be calculated for that one. So if you substitute these values in, okay, into your calculator, you get, for the first value, $3,787.43. For the second one, you get $3,573.05. For the third term, you get $3,370.80. And for the fourth deposit, you get $3,180. And remember, your fifth deposit, which was already calculated, was $3,000. So now, just like we've done in the past, you should be able to just add all of these up, and you should have your future value, right? Because now we've shifted each of these terms, each of these $3,000 deposits, to be at the same focal date. Okay, remember we talked about that in our previous unit. So if you add all of these up, you get $16,911.28. Okay? So our question is that correct? Right? I'm showing you this. It seems like it's a rather tedious process to do it this way. So it works. This answer is the correct answer, but is it the easiest way? Well, the answer is no, that's not the easiest way to do it. There is a formula for actually calculating the future value if you know it's an annuity. Okay, so remember, equal payments, okay? And in this case, we're looking at compounding frequency and payment frequency being the same. Okay, so I'm not going to explain to you how this formula was derived, but I do expect you to know how to apply it. Okay, so the formula for this is that the future value is equal to the payment, okay, or that equal payment. In the last case, the payment was $3,000. And that's multiplied by the same term you're familiar with seeing, 1 plus the periodic interest rate, so that's per compounding period. And that's raised to the exponent n, which is the total number of periodic payments. Okay. From there, you subtract 1, and you divide it by that periodic interest rate. So if you want to see whether the answer is the same, why don't we try doing with all of our numbers from last question. Okay. So if we did, we'd have our payment of $3,000. And that's multiplied by 1 plus 0.06. Remember, the interest rate was 6%. And n here is the total number of payments. So remember, we had 5 equal deposits. So n is simply 5. Minus 1 divided by the periodic interest rate, which is 0.06. And if you calculate that out, remember, it's important when you're placing it in your calculator that you do the brackets piece properly. You'll get the same number, $16,911.28. So notice from our previous slide how tedious it was to have every individual payment discounted to the future value, where instead in this formula, if we know that they're equal payments and we know how many payments there are and the interest rate, we can calculate it directly. So let's look at an example where we can actually use this formula, okay, instead of doing it the long way. So find the accumulated value of quarterly payments of $50 made at the end of each quarter for 10 years if interest is 8% per annum compounded quarterly. So a couple things to notice here. Again, I've only showed you ordinary simple annuities, but I want you to get it into your mind that you have to start recognizing these things to know what type of annuity it is. Okay, so remember, if it's an ordinary simple annuity, it means payments are made at the end of each quarter, okay, which it was. And if it's simple, it means that the payment frequency and compounding frequency are the same. Well, payments are made at the end of each quarter, and interest is compounded quarterly. So that means that they are the same, okay? Quarterly payments, quarterly interest calculations. So it is an ordinary simple annuity. Now, okay, if we know that, then we can start with our formula. We're trying to find the accumulated value, which in other words, you can say future value. So the future value, okay, is equal to your payment multiplied by 1 plus the periodic interest rate to the exponent n. Again, this n is the total number of payments, okay, minus 1 divided by the periodic interest rate. So, given in the question was our payment. So every quarter we're paying $50. All right. Our periodic interest rate, okay, we know our nominal interest rate is 8%, which is equal to 0.08. Okay. Our number of compounding periods per year, m, okay, is equal to 4. So our periodic interest rate, I, is equal to j divided by m, which is 0.08 divided by 4, which is 0.02. Now, n is the only thing that's different. It's the total number of payments. Okay, so you have to consider n is equal to the number of years times the number of compounding periods per year. The formula hasn't changed, okay, in this case, because the compounding frequency and the payment frequency are the same. Because every quarter you're making payments, which means each year you're making 4 payments a year. And in this case, it was given that it was for 10 years. So you can use this same formula. N is equal to the number of years, 10, times the number of payments per year. Okay, or in other words, the number of compounding periods per year, which is 4. So in other words, you're making 40 payments. So now that we know all of these variables, we can simply substitute each one of them in. So our future value is equal to our payment, 50, times 1 plus our periodic interest rate, 0.02, and that's the exponent 40, minus 1 divided by our periodic interest rate, 0.02. So if you calculate that out, again, this type of item you really need to practice placing them in your calculator to make sure that your calculator does the steps in the order that you want them to. Okay, so when you place this in your calculator, you'll get a final answer of $3,020.10. Okay, so quite a bit faster than our first example we did where we just tried to use our previous formula. Okay, again, I provide you with these formulas, but I do expect you to know how to apply them. Okay, so let's look at another example. You deposit $10 at the end of each month for 5 years in an account paying 6% per annum compounded monthly. Determine A, the amount of money in the account at the end of the 5-year term. B, how much of the amount in the account was actually contributed by you. And C, how much was interest earned. Okay, so there's a few more items I'm trying to have you find here. Okay, so, but the first question just asks how much money is there going to be in the account at the end of the term? Well, we're looking at this question, equal payments, the end of each month, okay, which makes it an ordinary annuity. And since you're paying monthly, your interest rate is also compounded monthly. So the compounding frequency and the payment frequency are the same. So this is an ordinary simple annuity. Right? So that means we're trying to find the amount of money at the end of the 5-year term. So the future value of this annuity. So your future value is equal to your payment times 1 plus I to the exponent n, I being the periodic interest rate, n being the total number of payments, minus 1 divided by the periodic interest rate. So this is part A, right? So we know that our payment is equal to $10. Our nominal interest rate is 6%, which is 6 divided by 100, removing the percentage sign, or 0.06. Our number of compounding periods per year, M, is 12, because it's compounded monthly. So our periodic interest rate, I, is equal to J divided by M, which is 0.06 divided by 12, or 0.005. So in this case, N, number of years, times the number of compounding periods per year, because again, the compounding frequency and the payment frequency are the same. So that's equal to 5 years times 12 payments a year, or 60. Okay? So we can substitute these into our formula. The future value is equal to 10 times 1 plus 0.005, our periodic interest rate, to the exponent 60, minus 1 divided by 0.005. Okay? If we do that, we get a future value of $697.70. So that's the total value of it. All right, but part B says how much of the amount in the account was actually contributed by you. Okay, so stop and think. You're putting in $10 a month, right? For 5 years. In other words, we made 60 payments. So the amount you contributed must simply be, okay, the $10 you contributed times the number of payments you made, which was 60. So that means that $600 of that $697.70 was contributed by you, because that's simply you taking $10, whether it's out of your wallet, every single month for 5 years and placing it in that account. Okay? Now, the opposite, what's the interest? Well, the interest must be the money you didn't contribute, right? So that must mean it must be the future value, the $697.70, minus the amount you contributed, right? Because you didn't contribute all of that money, because your future value is more than the amount of money you placed in it. So that means your interest earned must be $97.70. Okay, so all this question was doing was helping to break down what each item means within these calculations. So let's look at an application of it. Okay, I'm going to go in a little different direction. Jim set up a savings account at his bank where he deposits $300 at the end of each quarter for 8 years. After 8 years, he stops adding money and the money sits in the account for an additional 5 years. During the entire time period, he earns 5% per annum compounded quarterly. So part A, how much will be in Jim's account after the first 8 years? B, how much will be in the account after the additional 5 years is completed? Okay. The reason I'm showing this as an application is we look at each topic. Last unit we looked at compound interest. This unit we're looking at annuities, but they all play a role, right? You're seeing how these formulas use similar variables in their equations. So this question I like to start kind of with a graph. Okay, so he's got 1, 2, 3, 4, 5, 6, 7, 8 years. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, where he has an annuity. Then he's going to let it sit for 5 more years, 9, 10, 11, 12, 13. So 9, 10, 11, 12, 13. Okay, and this is today, year 0. So part A wants to know how much money is in the account right here. Okay, so that's at year 8. And part B wants to know how much money is in the account after it sat there for 5 years. So this is B, okay, and this is A. All right, well, let's look at the question. Again, I want you to start to get familiar with each of these annuity types. So He's depositing an equivalent amount of money, $300, okay, at the end of each quarter for 8 years. N means it's ordinary. Then you look, he's depositing it quarterly, and his interest is being earned quarterly. So that makes it a simple annuity. Okay? Those are the things to look for. So we know it's an ordinary simple annuity. Payments made at the end of the payment periods and compounding frequency and payment period are the same, in this instance both quarterly. So in part A, we're going from today, which is year 0, to 8 years down the road, right? Because that's the only period in time in this question where he's adding money, okay? So that period can be treated as an annuity. So we can find the future value, which would be the future value at year 8 or at the end of the annuity, okay, using our formula. So part A, future value is equal to our payment times 1 plus the periodic interest rate, the exponent n, remember the number of payment periods, minus 1 divided by the periodic interest rate. Okay? So a couple things we know in this question. Our nominal interest rate, J, all right, that's equal to 5%, which is 5 divided by 100, removing the percentage sign, or 0.05. M, in this case, the number of compounding periods per year, is equal to 4 because it's quarterly. So our periodic interest rate I is equal to J divided by M, or 0.05 divided by 4, which is 0.0125. Okay? Our last item that we need, actually there's 2 items that we need. Okay, the item I didn't write down, our payment, which was given in the question, $300. And our last item is our number of payment periods, N, okay, which is equal to the number of years multiplied by the number of payments he's making per year, or number of compounding periods per year. In this instance, because it's an ordinary simple annuity, those are the same thing. So N is equal to 8 years multiplied by 4 payments a year, which is 32. Okay? So if I substitute that in, our future value is equal to $300 times 1 plus 0.0125. That's the exponent, 32, minus 1 divided by 0.0125. Okay? So if we calculate that out, we get a future value of $11,715.13. Okay? So that is the value right here, $11,715.13. So now that's the present value at year 8, and we want to find how much it's worth in 5 years. Again, we don't have any payments, right? He's not adding any more money to it. So what this means is we want to just find the future value of that amount 5 years later. Okay? So if we do that, okay, this is just continuing on my graph. That means for part B, we should just be able to use the future value formula that we used in our previous unit. And that's because there's no payments being added. There's nothing else. We're just trying to take the amount of money he had at the end of year 8, okay, going back to our graph. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So, going back to our graph. So, we are currently at year 8, okay? And we know that he should have $11,715.13. Once his annuity is done, his term's done, he's not making any more payments. But now he wants to go 5 years in the future. So he wants to go to this point in time, just earn interest on it, right? You're still earning interest on this the entire time, okay? So he wants to know what that amount of money is. And like I said, this is just simply a future value calculation. So remember, future value is present value times 1 plus the periodic interest rate to the exponent n, and the exponent n in this case being the total number of compounding periods. So we know our present value is $11,715.13. Our periodic interest rate, remember, interest rate for this question was given for all periods. So our periodic interest rate won't change. It's still 0.0125. But our number of compounding periods will, right? So that's equal to the number of years times the number of compounding periods per year. So in this case, we're going from year 8 to year 13, so 5 years. And remember, in the question, interest was compounded quarterly. So this is 4, so that gives you a value of 20. So now we can simply substitute all these values in. So our future value is equal to $11,715.13 times 1 plus 0.0125, the periodic interest rate, to the exponent 20. So if you calculate that out, you get a future value of $15,019.23. Okay? So what this is showing, all right, is for the first piece you used an annuity, right? But each of these items are related, okay? Just because we did compound interest in the last unit doesn't mean you might not see those equations kind of sprinkling in as we do the rest of the items in this course, okay? Okay, let's look at one more example, which kind of, it's a more complicated example that puts a lot of these pieces together that we've been discussing. So Heather contributed $1,500 at the end of each year for 12 years into a savings account. Interest earned on the savings account was 4.5% compounded annually for the first 8 years, and then increased to 5.5% compounded annually. How much was the balance in the account 5 years after her last contribution? So a couple things we notice here. Regular payments at the end of each year. Okay, that makes it an ordinary annuity. And you'll notice that interest in both cases was compounded annually, and her payments were also annual. So that means it's an ordinary simple annuity. Okay? A trick in this question that you'll notice that we didn't have the last question was that her interest rate actually changed. It was still compounded annually, and interest rates do change, especially along, this many years. You think back to signing in on a mortgage. A lot of times you sign a mortgage at an interest rate for a certain number of years, whether it's 2 or 3 or 5. And then close to the end of that term, when you're discussing with your bank, you can either receive a higher or lower interest rate depending on how interest rates have shifted in that period of time. So this is actually an example that's somewhat common. Okay, and then normally your payments will change slightly, especially if it's a mortgage. So there's a lot of different things going on here. So again, I'm going to start with a graph. Okay, so this is year 0. Okay, so for the first 8 years, she had interest of 4.5%. So 1, 2, 3, 4, 5, 6, 7, 8. So this is year 8. And during that time, she had 4.5%. Okay, then for the rest of the period, she had 5.5%. Okay, so in her annuity, it was 12 years. So she's got 9, 10, 11, 12. Okay, so this is when her annuity ends. Okay, and then in the question, they want to know the balance 5 years after her last contribution. Okay, so that means we also have to go 5 years further. 13, 14, 15, 16, 17. So I start this question and you're already stopping and thinking, wow, there's a lot going on, right? So for the first 8 years, she earns 4.5% interest. Then she's going to earn 5.5% interest for the remainder of her annuity, okay, which was 12 years total. And then she's also going to have 5.5% interest for the remaining 5 years to find the balance. So the easiest way to break this down is to think of it as two separate annuity calculations. Okay, your first annuity calculation will be for today to year 8. So that I'm going to call that annuity calculation 1. Then when the interest rate changed, okay, your second calculation will be after year 8 to year 12 when the annuity is done. Okay, so you're going to come out with a number at year 8 for the first annuity and at year 12 for the second annuity. From there, all right, we then have to take that and say, okay, we want to know what the balance is 5 years after that last payment. So we need to again use, going back to compound interest, the future value formula for each of these two annuities, one that was done as of year 8 at the lower interest rate, and the other done as of year 12, where you did the last 4 years of the annuity as a separate calculation at a higher interest rate. Okay? So let's take a look at kind of what that means. Okay, so we've got two annuity calculations, which means we need the future value calculation for those annuities. Future value, I'm going to call it annuity 1. That's equal to your payment times 1 plus your periodic interest rate. Again, I'm going to write a subscript 1 because your interest rate is different. That's the exponent, n1, so the number of payment periods for this, minus 1 divided by your periodic interest rate, I1, for this annuity. Okay? That's for annuity number 1. So if we want to do the calculations for that annuity, okay, we know our nominal interest rate is 4.5%, which is 4.5 divided by 100, removing the percentage sign, gives you 0.045. Our number of compounding periods is simply 1 because it's annual. So our periodic interest rate, which is J divided by M, is 0.045 divided by 1, which gives us 0.045. Now, our total number of payment periods, she's paying it once per year. In this instance, we're only talking about the first 8 years, right? Because this formula has a certain interest rate. So we can't use both interest rates, right? So that's why I broke it up into two annuity calculations, all right? So N is equal to your number of years, 8, multiplied by the number of payment periods, okay, which was 1. So we get a value of 8. So I'm going to substitute those values into this equation. So future value 1 is equal to your payment, $1,500, provided in the question, times 1 plus 0.045, and that's to the exponent 8, minus 1, divided by 0.045. So if you calculate that value out, you get a value of $14,070.02. So that, all right, is the value of your first piece of the annuity right here, $14,070.02. Okay, so that's your first piece before the interest rate changed. So now we need to calculate the second piece of that annuity. Okay, so I'm going to switch to another slide, all right? And I'm going to I'm just going to put kind of our graph back up. So 1, 2, 3, 4, 5, 6, 7, 8 is where we are. 9, 10, 11, 12. Then we got to go 1, 2, 3, 4, 5. So I drew this line a little too long. Let me just fix it. So we have found at year 8 this first piece of the annuity, right? And that was $14,070.02. Now we need to find the second piece, right? For the next 4 years, how much that is worth, okay, given the new interest rate of 5.5%. Okay? So let's find that value next. It's the same formula. Future value is equal to our payment times 1 plus, I'm going to call it I2 because it's our second part of our annuity calculation, and N2 minus 1 divided by I2. So in this case, we know our payment is still the same, is $1,500. Our nominal interest rate has changed to 5.5%, which is 0.055. Again, our value for M is not changed, it's just 1, it's annually. Remember, because the compounding period frequency and the payment period frequency are the same, because this is an ordinary simple annuity. So our periodic interest rate I is equal to J divided by M, which is 0.055 divided by 1, or just 0.055. Lastly, our number of payment periods, well, we're going 4 years, and our payments are annual. So 4 times 1 is just 4. So our future value for our second annuity is 1,500 times 1 plus 0.055 to the exponent 4. Okay, I'm just substituting the values in, minus 1 divided by 0.055. Okay? So our future value for this second piece of our annuity is $6,513.40. So that's the value for that second piece of our annuity. That's the value at the end, $6,513.40. Now, we've got our first piece of our annuity, which we calculated for the first 8 years, and our second piece of our annuity calculated for the last 4 years. So we want to know what it's worth all the way down here. All right? So in order to do that, we have to do a future value calculation for each one of these numbers. Okay? Because remember, back to our compound interest, we had to pick a focal date. So the focal date for this, so that all the money is in the same terms, okay, is that year 17, right? So 5 years after her last contribution. So we've got 2 calculations we need to do, both of them being future value. Remember, future value for compound interest is present value times 1 plus the periodic interest rate to the exponent n, this n being the total number of compounding periods. So that's going to be for both the first annuity calculation and the second annuity calculation. And I'll call those N1 and N2, okay, as well as present value 1 and present value 2. So what values do we know? Okay, we know present value 1 and present value 2. Present value for the first annuity is this $14,070.02. And for the second annuity, it's the $6,513.40. Other items that we know is we know the periodic interest rate. It hasn't changed in this question. Okay, so it stays at 0.055. But what's different is our number of compounding periods for each, right? Because one has to be brought forward by 9 years from year 8 to year 17. The other one has to be brought forward 5 years from year 12 to year 17. So we know present value 1 is $14,070.02. Present value 2 is $6,513.40. Periodic interest rate has not changed, 0.055. So N1 and N2, N1, okay, we've got to go from year 8 to year 17, so 9 years times 1 payment a year, or 1 compounding period per year, right, because it's annually. So that's 9. And N2, we have to go 5 years from year 12 to year 17. So 5 times 1 is just 5. So now we can substitute all of these values in and then just add these two together, right? Because then they're both at year 17. So our future value 1 is $14,070.02 times 1 plus 0.055, okay? And that is to the exponent 9. And our future value 2 is $6,513.40 times 1 plus 0.055 to the exponent. Oh, sorry, 5, because we're going 5 years. Okay, so I'm running out of space, but I'll write them down here. If you calculate these out in the calculators, the future value for the first one is $22,780.69. And for the second one, it's $8,512.75. So both these have now, you've found the future value all the way up to year 17. Okay, so we can simply add these together to know what the total value is. And if we do that, okay, I'm just going to add these together, we get a total of $31,293.44. So I know that there was a lot of information to take in and how we did these steps, but just I stress that you should watch this example more than once. All right, try this example out yourself, maybe before you watch it, but the steps are always the same, right? We're still looking for a certain focal date. All right. In this case, because the interest rate changed, we actually had to do 2 separate annuity calculations. So it's a more time-consuming version of this calculation. Okay, so I'm going to stress it again. It is really important that you keep trying these examples. Okay, if you do have a copy of the textbook, I encourage you to use the some of the example exercises at the end of the chapter, which I go over at the end of the lecture as well. The way to improve on these is practice, okay? Practice, practice, practice. All right, so everything we talked about was for an ordinary simple annuity and finding the future value. So now I want to work backwards. I know how much my investment's worth in the future. Can I find the present value? All right. So just like we did with future value, well, you stop and think, okay, I've got this graph, all right, and I've got these regular payments, whether it's $100. Can I just discount all of them back using the same present value formula? Remember, present value is future value divided by 1 plus the periodic interest rate to the exponent n. Can I just use that formula for each one of these values? Well, we're going to find out that the answer is yes. Okay, but again, just like in the past, it's a more tedious process. All right. So for this, keep in mind it's still an ordinary simple annuity. So what that means is that the payments are at the end of each payment period, just like it has been. And your compounding frequency and your payment periods or payment frequency, again, are the same. Okay, so that's, I like to point that out in each of these questions too, right? Because this is only the first instance of an annuity that we're going to look at. All right, so it's going to be important moving forward that you can recognize those differences in the questions, okay? So let's look at an example. Again, I'm going to use the present value formula to try and find the answer to this. Find the present value of an annuity with payments of $3,000 at the end of 5 consecutive years if interest is 6% per annum compounded annually. So a couple things to notice. Payments are made at the end of each year, which means it's annually, and it's compounded annually. So this is an ordinary simple annuity. All right. Regardless, I'm going to show you it using the present value formula. So we'll start, okay, here's where we are, year 0, and you're making payments the end of year 1, year 2, year 3, year 4, and year 5. So 5, 4, 3, 2, 1. Okay, and at the end of each of these, you're making $3,000 payments. Okay, so just like we did with future value, except we're going to work backwards. So we should be able to find the value if we find the present value of all 5 of these payments, again, making sure we pick today as the focal date, okay, because we're looking at the present value, okay? So, a couple things we know. We know we're doing 5 different calculations here, okay, and then we're going to be able to add each of those up. So, remember the present value is equal to the future value divided by 1 plus the periodic interest rate to the exponent n, being the number of total number of compounding periods. All right? So what we know in every single case, I'm going to do this off on the side, is our future value for each of the payments is $3,000. Okay? Our nominal interest rate, J, is 6%, which is 6 divided by 100, removing the percentage sign, or 0.06. M, our number of compounding periods per year, it's given in the question as annually, so M is 1. So our periodic interest rate, I, is equal to J divided by M, which is 0.06 divided by 1, or 0.06. Now the only difference for each of these questions is going to be, again, our net total number of compounding periods. So I'm going to go in order and do N1, N2, N3, N4, and N5. And these numbers, just like they did in the past, correspond with the numbers for each year. Okay? So for N1, all right, it's 1 year in the future. Whoops, wrong color. 1 year in the future, and again, we only have 1 compounding period per year because it's annually, so that's 1. And 2 is 2 years times 1, which is 2. And 3 is 3 years times 1 is 3. And 4 is 4 years in the future, so 4 times 1 is 4. And lastly, N5 is 5 years in the future, so 5 times 1 is equal to 5. Okay? So we just have to do these calculations for each of the 5 payments. Substituting all of these values in, I'm just going to erase our formula. So we have present value calculations 5 times. Okay, present value for item 1, okay, is 3,000, just divided by 1 plus 0.06, and that's to the exponent 1, okay, and that gives $2,830.19. For deposit 2, it's 3,000 divided by 1 plus 0.06, and that's the exponent 2. Remember, we're 2 years in the future. And that's $2,669.99. For year 3, we have 3,000 divided by 1 plus 0.06 to the exponent 3 for 3 years, which is $518.86. For number 4, okay, we have 3,000 divided by 1 plus 0.06 to the exponent 4, which is $2,376.28. And lastly, for our 5th deposit, we have 3,000 divided by 1 plus 0.06 to the exponent 5. And we get $2,241.77. So we have them all discounted to the same focal date, which is today. So now you can simply add it together. So the present value is equal to $2,830.19 plus $2,669.99 plus $2,518.86 plus $2,376.28 plus $2,241.77. And if you add all those numbers up, you get $12,637.09. So that is the present value of this investment. Okay? It's, again, a very long and tedious process, right? So some of you, knowing that these are videos, have probably already skipped this, saying you're probably thinking you don't want to see it, and you want to go to the formula. If you didn't do that, then thank you. I just wanted to kind of show you this before I give you the formula. So just like with future value, there is an easier way to do a present value calculation. Okay, so it's similar, looks similar to the future value formula. It's a little bit different. Again, it's derived using a lot of what we used for compound interest. So I'm not going to go into how this formula was derived, but I do expect you, again, to know how to apply it. So for the present value, it's equal to the payment, and then it's multiplied by this item in brackets, 1 minus, okay? In this instance, it's 1 divided by that familiar term that we've seen, 1 plus the periodic interest rate to the exponent n. Again, for annuities, n is the total number of payment periods or number of periodic payments. That's divided, okay, by the periodic interest rate I. Okay, so it's similar, but looks a little bit different than future value. So let's look at an example to see how we can apply it. So find the present value today for an annuity with payments of $50 made at the end of each quarter for 10 years if interest is 8% per annum compounded quarterly. Again, I want you to be familiar with this. It's saying at the end of each quarter, and interest is compounded quarterly. So payments being at the end means ordinary. And because the compounding frequency and the payment frequency are both quarterly, so they're the same, it means it's a simple annuity. So it's an ordinary simple annuity. Okay? So let's start by looking at the formula. Okay, we know we're asking for present value. So present value is equal to the payment times 1 minus 1 divided by 1 plus your periodic interest rate to the exponent n. Okay, and that's again divided by your periodic interest rate. So now we just need to figure out each of these variables. Okay, so we know the payment is $50. It's provided in the question. We know our nominal interest rate is 8%, okay, which is 8 divided by 100, removing the percentage sign, or 0.08. And we know the number of compounding periods is 4, because it's given in the question that it's quarterly. So our periodic interest rate I is equal to J over M, or 0.08 divided by 4, which gives us 0.02. Now N, our total number of payment periods, okay, it's going for 10 years, and we have 4 payments a year, right, because he's paying at the end of each quarter, so N is 40. So given all this, we can simply substitute it in. The present value is equal to our payment, 50, times 1 minus 1 over 1 plus 0.02, remember 1 plus our periodic interest rate, to the exponent, 40. It's a bad 40. Let me just erase it, write it a little bit better. Divided by our periodic interest rate, which is 0.02. So if you calculate that out, you get $1,367.77. Okay? The main trick with this, you saw how much faster it was in the long example that we went through using the present value formula. I mean, for those of you that watched it and didn't skip right to this formula piece in the video. But the one thing to keep in mind is that this item in the brackets, okay, is making sure you get used to putting that in your calculator correctly so that it does the order of operations in the way that you want it to. All right. So let's look at another example. Marcelo obtained a loan which he paid back with payments of $288 at the end of every 3 months for 3 years. Interest was 8.4% per annum compounded quarterly. So part A is how much money did Marcelo borrow? And part B, how much interest did he pay on the loan over the 3-year period? Okay, so there's a couple things to notice here. First of all, Okay, so at the end of every 3 months, which is quarterly, and interest is compounded quarterly. So it's an ordinary simple annuity. Okay, and we're asking for how much he borrowed. It's giving us his payments that he paid back. But remember, if you're borrowing and taking out that loan, you're taking out the money at the start. So that means we need to find the present value. So in part A, if we want to find the present value, it's equal to the payments that he made times 1 minus 1 plus the periodic interest rate to the exponent n, right, the total number of payment periods, divided by the periodic interest rate. So we know his payments, okay, are $288. His nominal interest rate is 8.4%, which is 8.4 divided by 100, removing the percentage sign, 0.084. The number of compounding periods per year, M, okay, is 4 because it's given as quarterly. So our periodic interest rate is J divided by M, or 0.084 divided by 4, which is 0.021. Lastly, our value for N, okay, well, we know that's 3 years, given in the question, and his payments are quarterly, so 4 payments a year. So in total, he's going to make 12 payments, okay? Substituting all of these values in, your present value is equal to your payment, $288, times 1 minus 1 divided by 1 plus 0.021, and that's the exponent 12, divided by 0.021. So your present value comes out to $3,027.08. So that must be how much Marcelo borrowed. Okay? Part B is how much interest did he pay on the loan? Well, stop and think. His loan was $3,027.08, but he actually paid the amount paid. He paid $288 back, and he paid it 12 times because he made 12 payments. So the amount he actually paid them was $3,456. So that means the difference between what his present value is, or the amount he took out as a loan, and the amount he paid must be the interest he paid on the loan. Okay? So if you do that, you get $3,456, the amount he paid, minus the amount he borrowed, $3,027.08. You get $428.92. Okay, so that is actually how much interest he paid on that loan. So it is quite a bit of money when you consider that he only took out $3,000 for a period of 3 years. So let's look at our last example for this lesson. So this one's going to make you stop and think a little bit, especially when we get to part B. Jen borrowed money from her bank and agreed to repay it with installments of $161.75 per month over 4 years. The interest is 9% per annum compounded monthly. Part A, how much did Jen borrow? So, just like the last question, this piece seems pretty well straightforward, okay? Means we need to know how much she borrowed. She's paying it back in installments, so we need to find the present value. So for part A, present value is equal to your payment multiplied by 1 minus 1 over 1 plus your periodic interest rate, it's the exponent n, divided by your periodic interest rate. Okay? So what that means is we need to figure out what some of these variables are. First of all, you know your payment is $161.75. You know that your nominal interest rate is 9%, which is 9 divided by 100, removing the percentage sign, which is 0.09. You also know that it's compounded monthly, so M must be 12. So that means you could find your periodic interest rate I, which is J divided by M. or 0.09 divided by 12, which gives us 0.0075. Lastly, n, okay, we know that it's over 4 years, and we know that we have 12 payments a year, right? Because it's provided in the question that it's monthly. So n is 48. So you can calculate your present value, okay? So it's 161.75 times 1 minus 1 over 1 plus 0.0075, the exponent 48, divided by 0.0075. So calculating that out, her present value is $6,499.89. So that's how much money Jen borrowed. So that's part A. Part B is, what if something changed? What if Jen did not make her payments for the first year, and now the bank is demanding that her entire loan was paid? Okay, so then how much at that point in time would she have to pay? So we're going to look at this. I'm just going to transfer some of this over to our next slide. So looking at what we had on the last side, we know that her present value was $6,499.89. Another thing we know is if she didn't make her payments for the first year, right, she has to then make those payments eventually. So I'm going to start with a graph, okay? So year 1, year 2, year 3, and year 4. So if we're at time 0, okay, and she hasn't made any of these payments, okay, that means we're now at year 1, and she hasn't made any of these payments, which means if you don't make that payment, it means you're going to continue to accumulate interest on it. So in part B, there's kind of two parts to it. There's the before our time period, right? Because right now we're a year in and Jen hasn't made any payments. And then there's the after. There's the 3 years remaining on her loan, okay? So there's two aspects to this question. The first aspect is if she missed all those payments, we have to find the future value of that first year of the loan back to, so that we're in year 1. Then we have to find the present value of the remaining loan back to that point in time to figure out how much she owes, right? Because she's missed these payments, okay, that number should come out as a higher value, right? Because she's now, the bank will want to earn interest on the money she didn't pay as well. So we have to do two calculations. We have to do a future value and a present value calculation. So we'll start by doing the future value calculation for the first year. So remember from earlier in this lesson, future value is equal to, whoops, not the present value, equal to the payment times 1 plus your periodic interest rate to the exponent n minus 1 divided by your periodic interest rate. Again, I don't expect you to memorize these formulas. You might have to jump back a couple sheets to find that formula. But I do expect you, like I said, to know when to apply them. So we need to start figuring out what some of these values are. Our payment, in both cases, doesn't change. It's still $161.75. Our interest rate also doesn't change. Okay, so our nominal interest rate, again, was 9%, which was 9 divided by 100. Removing the percentage sign was 0.09. M was still 12, right? None of this changed. We still have monthly payments, monthly compounding. So our periodic interest rate, which was J over M, is 0.09 divided by 12, or 0.0075. The only thing that changed, okay, is N, okay? So our value for N, we're only going 1 year, right? Because we're 1 year into the loan, right at this point in time. Jen hasn't made her payments, okay? So that means that period of time, it's been 1 year multiplied by 12 payments a year. Or in other words, N is 12. Okay? So we can substitute those in to find our future value. So our future value is equal to 161.75 times 1 plus 0.0075 to the exponent 12 minus 1 divided by 0.0075. And if we calculate that out, we get a future value of $2,023.10. So that's the value of that at year 1, right? So we found the future value to figure out of that piece of her loan she hasn't paid, how much is it worth at year 1. The second piece is the same as what we did in part A. Okay, we need to find the present value, except this time we're finding it at year 1. So now we have a condensed time period of only 3 years. Okay, so for that we need our present value formula, which is our payment times 1 minus 1 over 1 plus the periodic interest rate to the exponent n divided by the periodic interest rate. So the payment didn't change, the periodic interest rate didn't change, but what did change was the value for n. All right, so in this case, I'll do it in green. N is equal to, we have 3 years, but we still have 12 payments a year. So in this instance, n is 36. All right, but the other values didn't change. The payments are still 161.75, okay, and our periodic interest rate is still the same, 0.0075. So if we substitute these values in, we get 161.75 multiplied by 1 minus 1 over 1 plus 0.0075 to the exponent 36 divided by 0.0075. Okay, so if we calculate that present value out, we get a value of $5,086.52. So that's the present value of her remaining loan. So to figure it out, the question said they're demanding her entire loan was paid. They've had enough of the fact that she didn't pay her loan. So now you have to add these two numbers together. The amount she hasn't paid, okay, that she should have paid, which was that future value calculation, plus the present value of what she has outstanding in the loan. So the total must be equal to the $2,023.10. That was our initial future value calculation, plus the present value calculation, $5,086.52. And if you add those up, you get a value of $7,109.62. And that makes sense, right? Compared to our first value, okay, that was the original loan, that she's earned all the additional interest by not paying her loan off. Okay, so you stop and you do a kind of reality check and think, does that number make sense? Okay, the bank always wants to get their money. So again, I've been going through this lecture. You might want to watch it in parts. I know it's a long lecture. It's about probably an hour and 20 minutes. But I do recommend you start looking at practice problems. You can look over these problems I do more than once just to get more familiar with them. With these, it's really important. Practice, 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 right? Because there's a lot of steps. So if you do have questions, you're always free to send me an email or you can send me a message if I see it in Microsoft Teams. But email is definitely the best course to ask questions. So thanks, everybody.